It turns out that extensive form games with imperfect information give rise to subtly different classes of strategies. And in particular, one can make a distinction between behavioral and mixed strategies. And they're fundamentally very simple to explain. A mixed strategy is what is defined in a completely standard way. We have a notion of a pure strategy, that is what each agent needs to do in all of their information sets, and that is a unique action in each of those information sets. And a mixed strategy is simply a distribution over such pure strategies. A behavioral strategy is subtly different. It says, rather than start with pure strategies, it simply says, in each information set, how should you randomize? It may seem like the same thing, but it really isn't. And let's look at an example. So take this tree. And here's an example of a behavioral strategy. Player 1 can take action A with probability 0.5 and G with probability 0.3. What does that mean? That over here they'll randomize 0.5, 0.5, and over here they'll randomize 0.3, 0.7. That's a behavioral strategy. Similarly, a mixed strategy here would be something like the following. It says, let's look at two pure strategies. For example, A, G, there'll be one pure strategy, and BH would be another pure strategy. And let's look at some convex combination, some mixture of the two, 0.6 of the one and 0.4 of the other. That would be a mixed strategy. Now, although they are defined quite differently, one looking at the example might think that, well, one could really do the job of the other. And in fact, you'd be correct in this case. In a very famous result, a paper by Kuhn from 1953, it was shown that in certainly all these games of perfect information, mixed strategies and behavioral strategies can emulate each other. There's no the equilibria in mixed strategies are outcome equivalent to the equilibria in behavioral strategies. In fact, it's not true only for games of perfect information. It's true for games of imperfect information, that is, games with information sets where agents don't have full knowledge of where they are, so long as those games have what's called perfect recall. A game of imperfect information has perfect recall if, intuitively speaking, the agents have full recollection of their experience in the game. That means that wherever they are in each information set, they know all the information sets they visited previously and all the actions they've taken. To see an example of a game without perfect recall, consider the following game. So player 1 has here two nodes, this node and this node, and he cannot tell them apart. And you can think of it as basically sending two agents on your behalf to play, and neither agents know which of the two places it landed in particular what the other agent did. Regardless of your interpretation, it's the case that in a behavioral, so first of all, what are the pure strategies in this case? Well, the pure strategies for agent 1 is simply L, and one can, in this information set, either do L or R. So you'd either do L, which means you'd go here depending on where you were, or do R and go here depending on where you were. This is for agent 1. And for agent 2, there are again 2 pure strategies. So what would be a mixed strategy equilibrium in this game? Well, that turns out to be fairly easy to analyze. And we start with the observation that player 2 has a dominant strategy. Play down. And so no matter what the other player does, player 2 is no worse off and in general better off by playing D rather than U. And so a best response for player 1 to player 2 playing D is playing R, because they would get a payoff of 2 rather than a payoff of 1 if they played L. And so LD is in fact an equilibrium in this game. Notice the sort of the ironic or disconcerting fact that you have a very high payoff that is actually not accessible under mixed strategies. And that will be a hint about what's going to happen with pure strategy, with behavioral strategies. So what would an equilibrium in behavioral strategies look like here? Well, to start with, note that nothing has changed for player 2. They still have a dominant strategy of D, and let's assume they play that. What about player 1? No, player 1 has the opportunity to randomize afresh every time they find themselves in this information set. So let's assume they randomize somehow going left with probability P and right with probability 1 minus P. What, assuming player 2 plays D, what is their expected payoff given the parameter P? Well, with probability P times P, they will end up here and get a payoff of 1. So that's P squared times 1. With probability P times 1 minus P, they will end up here and get a payoff of 100. So that's 100 times P times 1 minus P. With probability 1 minus P times 1, they will end up, because this player 2 is not randomizing here, with probability 1 minus P, they will end up here and get a payoff of 2. That's 2 times 1 minus P. So this is their overall payoff, assuming they randomize P, and we simplify it to this expression. And we simply look at the maximum here of this this equation, and the maximum is arrived at this value. So with probability slightly less than half, they go left, and slightly more than half, they go right. That is player 1. And so we end up with this equilibrium where the player 1 randomizes this way and player 2 plays down with probability 1. So we see that the equilibria with behavioral strategies is when we have imperfect recall, as we have here, can be dramatically different than the equilibria with mixed strategies.